Hello, welcome to this lesson on measuring light. Question of the day. What's the wavelength of a wave? And which EM wave has the shortest wavelength? Back in the atomic unit, you learned about exciting electrons. Light is just a form of energy. Energy usually that we can see as opposed to feel. In chemistry, most of the time when we say, oh, light, we're talking about visible light, okay? Light that emerges when the electron is um, falling down to the ground state after it has been excited. Visible light, remember, is the rainbow colors spectrum. You are going to have a wavelength from like 400 nanometers up to 700 nanometers. This kind of skews a little bit. Some say 750 or 380. It kind of depends. But regardless, we're talking about visible light, all of the rainbow colors. So you should remember that if you have a sample of matter, you can get the electrons in those atoms to jump up to higher energy levels by giving them energy. And typically we're going to do that in a flame test by adding heat, or we'll have the gas sample in a tube and we give it electricity like a neon light. And that added energy is going to make the electrons go, ooh, there's a lot of energy here. And they are able to jump up to higher energy levels because they have enough energy to pop away from the attraction they have to the nucleus of an atom. Remember, the nucleus is where protons and neutrons are. Protons are positive, electrons are negative. They're attracted to each other. Think of it kind of like magnets. You need energy to pry apart magnets, and this amount of energy that you're adding to the matter is able to pop the proton and electron away from each other. Protons can't move, they're locked in the nucleus, so the electron is going to have enough energy to overcome that attraction, jump up to the excited state, but eventually that nucleus calls, the proton calls, and the attraction is right back. And as that electron falls back to the ground state, like this is showing right here on the right, the electron falls to the ground state. The energy in the form of visible light is going to come out of the matter, and we are going to see the beautiful colors of a flame test, or we are going to see the colors as the gas glows in the spectral tubes. Again, speaking of attraction, protons and electrons are attracted to each other, but protons cannot move. So the proton will just call out, hey, I'm positive, come back. And the electron goes, oh yeah, I'm negative, I'm attracted to you. And we'll come back to ground state. Now, the law of conservation of energy, we're going to talk more about later in the course, but it is a staple of science. Energy is conserved. So the amount of energy that the atom absorbs to get that electron to jump up is going to be the same amount that falls back. That will be released when the electron falls back, rather. So it's going to absorb energy, heat, and electricity, which we can feel but can't necessarily see. I mean, you can see a fire, but you're seeing the light energy of the fire. The heat is really what's forcing the electron to rise to the excited state. And let's just say, for the sake of argument, it absorbs 100 joules of energy. 100 joules of energy are going to pop back out in the form of visible light when the electron falls back to ground state. Now, the flame test is really cool. Girl loves a flame test. It's my favorite part of chemistry, honestly. Even more so than like making ice cream in a Ziploc bag. I love the flame test. Flame test is cool because every electron combination is going to have a different flame test. So lithium has 3 electrons. Where they jump is pretty like characteristic. They jump up, they fall down, and then you're going to get this like bright pink flame. Sodium and calcium are kind of boring, honestly, because they look just like regular fire all the time. Potassium has a beautiful lavender flame. Copper is my favorite flame of all time. It's this beautiful, like it looks like the is it patina? The green blue that you'll get on like a really old penny. It's that beautiful color. It's a lot of fun. They actually sell most of the time it's at like a hardware store, but sometimes you can get it at like Walmart, other places, summertime, with the s'mores stuff. If the store knows what they're doing, they will put marshmallows, chocolate, and graham crackers all together on the shelf with the marshmallow fork sticks, right? They have like the prongs on them. And sometimes they'll have these cool things, and they're packets of like copper salt, basically. And you sprinkle it on your fire, and you can have like this beautiful blue green fire while you're roasting marshmallows. Now, copper is more or less safe. So if you got it on your marshmallows, it's not the end of the world. But you wouldn't want lithium on your marshmallows. So this is why we don't roast marshmallows on a Bunsen burner, because a lot of the time you have these salts make a mess with your Bunsen burners. Some salts are okay, like copper. So here we have an example of a flame test. I can't see the sample. The sample is probably a popsicle stick that I have soaked in. This is probably lithium. Lithium dissolved in water. And then that popsicle stick goes into the flame, and you can see the Bunsen burner flame's usually blue. We have like this very pretty pink color. Or this I know is hydrogen. This is hydrogen gas inside a tube. That tube, I plug it in, it gets a bunch of electricity, and then these electrons are just bouncing up to excited. They fall to ground, and they give this beautiful light. And all of the electrons are like, one's in excited, the next one is in ground, and it's not like it's flickering. It's so many electrons doing it all at once that they're not working in unison, is my point. It's not flickering because it's ground, excited, ground, excited, ground, excited. This guy is ground while this guy's at excited. So at a molecular level, sure, it's flickering, but you can't see it with your eyeballs. But this is what it looks like when our electrons are jumping around. They're absorbing heat, they're putting out visible light, they're absorbing electricity or putting out visible light. And it's a beautiful thing. This is how fireworks is made too. So we have this tool called a spectroscope, which you can, I don't have mine right here in front of me, but it's like a little, some of them are nicer than others. The cheap high school chemistry lab ones that you would use are probably this long. They're like triangle shaped, and it's like a little plastic telescope, sort of. It doesn't actually telescope, but you put it just to one eye. It's called a spectroscope, and it can measure the wavelength of the light that you're looking at. So typically you would do these in a dark classroom. You would cover up all the windows, turn off the lights, even like the computer monitor gets turned off because it can interfere with the light in the room. You take this spectroscope and you are going to point it at the light. And with that, you can measure the wavelength. So because we have a measured wavelength and we know the speed of light, we can do some math to figure out what the frequency of that wave is. Okay, so we have our radiation. We're pointing the spectroscope at a sample of matter. We are going to read the spectrum is what it's called. And because there's spectral lines somewhere on the spectrum of visible light. And we're going to get, this is a computerized version. You would get like a readout. Most high school chemistry labs, you're going to read it. It's kind of like reading a ruler. So this is the inside of a spectroscope. And it's being pointed at that hydrogen from before. So I have this, I actually put my phone camera up to it. I'm pointing the camera at the hydrogen, and I'm seeing this pink light. And the pink light is a combination of a lot of wavelengths, but it's really just these three primarily that were able to be measured. So we have one at like, this is nanometers across the bottom. So this 7 is really 700 nanometers. This 6 is 600 nanometers. This line, the solid line would be 550. The line between 5 and 6 would be 550. And each of the dashed lines represents 10 nanometers. So this red line looks like it's coming in at 670. The teal blue is exactly 500. And this violet line looks like 450. Maybe that's indigo. Ask Isaac Newton. So this is what the inside of the spectroscope would look like. You read out your measurements. This pink light is a combination of red, blue, and purple, and that sort of makes sense. So nanometers. Nanometers are itty, 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 bitty. They represent 1 billion nanometers. And in scientific notation, that would be 10 to the ninth nanometers is 1 meter. And just to like put it into perspective, a strand of DNA is about 2 nanometers across. So that can kind of help you. So we're reading wavelengths that are, 750 nanometers. Teeny weeny, teeny weeny. So practical uses of spectroscopy, which is what this entire science is. We can measure light for a lot of different reasons, one of which would be to learn about atmospheres and compositions of planets really, really far away. Because a spectroscope, as long as you block out all interference, you're just reading light. And the light does not have to be on the lab bench right in front of you. It could be all the way out in outer space. And this is how we learned that the sun was primarily made of hydrogen and helium. We did not send a little probe out to the sun to just go like capture a little bit of sunlight and figure out what it was. We did it from Earth with a spectroscope. So we use it for that. We also can use it in a chemistry lab. If we're not really sure what something is, you dig it out of the stock room, you do a few tests on it, and you're like, okay, there's no vapors coming out of it that are going to poison me. It doesn't react with air or water. Let's do a flame test and read the spectral lines and see what we can get. It's not a common way that we do things, by the way. But if we have spectral lines, we can kind of dissect them and figure out what we're looking at. So this sample of unknowns here is, I don't know what this is. Let's throw it on the flame, read it with a spectroscope, and we get these lines. We're getting 6 lines in total here. Then what I do is I'm going to pull in reference materials and try to match up some spectral lines. So when they did this with the sun, they were like, okay, those are the lines for hydrogen. That makes sense. Okay, there's a tiny bit of gold. There's a tiny bit of lithium. There's a tiny bit of carbon. They're finding everything. And then they found these lines and they were like, what do these lines belong to? They don't belong to anything we've ever seen before. And I said, oh, that must be a new element, helium. And then later they found that element on Earth and they matched it up and they were like, yep, that's helium. Helium was hard to find on Earth because it's very, very, very not dense. So it floats away really before it's ever captured and it doesn't react with anything. So it's very difficult to find it. So anyways, if we have this sample of unknowns, we got 6 lines here. We go, okay, what's in this? Well, if we match these 3 lines that are sort of close and clustered, those match up with fluorine. So fluorine must be in this sample. And these remaining 3 lines match up perfectly with the lines for lithium. So I must be looking at lithium fluoride. Okay. So that is how we would use these spectral lines. And this one is in black and white. The 400 area is your purplish area, and then we creep into blue, green, yellow, orange, and red is going to be at the bigger end. So looking at this, it would be warm colors. It would be like a yellowy orange. I'm not totally sure of the color. And that is how we use spectral lines. So all of this is really just measuring light. We will get into the calculations in the next lesson because when you are doing a lab, the first thing you do is take all the measurements and then you go through and do all the calculations. So here, again, the spectroscope, the high school level ones, you just read them like this. You read them manually. It's really just like reading a ruler. You just line up the lines. That's all. The big thing is watching for interference and understanding that the energy goes in to the atom. That electron now can overcome the attraction of the nucleus, the protons in the nucleus, rise up to the excited state. And when they come back down, they got to get rid of that energy. They have to offload it. So that energy comes off as visible light that we can see. So we would see this pink light, and then we can use a spectroscope to figure out exactly what wavelengths are composing that pink light that we're seeing. So that's everything. If you have any questions, of course, feel free to leave them in the comment section below the video. Subscribe so you don't miss the next lesson because we're doing those calculations and I promise they're not as scary as you may think. And I'll see you in the next lesson. Bye.